Okay, so we're going to look at some examples of arc length on a circle, some applications. So these are really more examples after my lesson video, so you can look in the link below. I really break down kind of how to approach arc length in that video, and in this video I'm just going to kind of fly through a few more examples related to what we were talking about. So these are the three that I'm going to go through. If you want to fast forward to find the one that you're interested for, you can pause if you want to read them. Okay, so let's start with the first one. So Charleston, South Carolina, and Toronto, Canada are 1,100 kilometers apart and lie on the same north-south line. If the latitude of Charleston is 33 degrees north, what is the latitude of Toronto? Okay, so I talked about latitude problems in my other video. And so the idea behind this is, so let's say this is the Earth, and you have to know a little bit about Charleston versus Toronto. I hope you know that Toronto is north of Charleston. So I don't know exactly where they are, but let's just say, like, as far as the location goes, we just want to put Toronto somewhere above Charleston. So we talked about kind of diagramming this way in the other video if you want a full breakdown. All right, so I know that from the equator to Charleston, this is a 33-degree angle. And so I'm trying to figure out what is this other angle here with Toronto. Okay, now the other thing I know is that this distance here, this is 1,100 kilometers. And I also want to just point out, in an earlier problem, this is like a thing that you just kind of know going forward. The Earth's radius is 6,400 kilometers. That's actually needed to solve problems like this. Okay, so how does this all relate to arc length then? Well, we are actually being given the arc length in this case, right? And then we know the radius. So we can figure out, if I know this arc length here, I can figure out basically like this little sliver in here. And if I know this sliver, then I can add that to 33 degrees to get all of what the latitude of Toronto is, right? Okay, so I have 1,100 for my given arc length. The radius of the Earth is 6,400, and then I just end up with theta. Okay, so theta will come out to 11 over 64. And what is that? Remember, that is radians. Very important with these types of problems because latitude is in degrees. So now we're gonna have to get this to degrees, right? Okay, so anyways, this theta, like I said, it is this little piece in here. So let's figure out what this is in terms of degrees. So we'll convert this to degrees. So I take my 11 over 64 radians times 180 degrees over pi radians. Bada bing, bada boom. I get 9.8 degrees. And so then to get my latitude, I can take the 33 and then the 9.8, and that will give me 42.8, and that is going to be the latitude of Toronto, about that. Okay, so moving on to B here. So this is another wheel problem, slightly different from the other one I talked about in my first video. Okay, so find the radius of the larger wheel in the figure if the small wheel rotates 75 degrees when the large wheel rotates 45 degrees. Okay, so here's the thing you have to really buy into to understand how to approach these problems. As both wheels rotate, they travel the same amount of arc length, right? Right. So also these wheels must have like tiny little ridges on them or something so that they can spin one another. So I kind of just drew this picture with my computer, but that's something you kind of have to assume. Okay, so this is super important though, that you understand that just as far, like, so this wheel could spin multiple times, but like the amount of arc length that it's traveling is equivalent to the amount of arc length that this one is traveling. If you get that, then you can kind of see how to move forward with this. So of course we have to convert from degrees to radians if we want to use our arc length formula. So I can go ahead and convert my 45 degrees. And so I get pi over 4 radians. And then when I convert the other one, 75 degrees. If I convert that one, I get 5 pi over 12 radians. Okay, so very important, very important that you label this right. I actually did this problem earlier and then I realized I did not label them right and it threw the whole thing off. Okay, so remember, the small wheel rotates 75 degrees, the large wheel rotates 45 degrees. So let me place these in the appropriate spot. The pi over 4 goes with the large wheel, and the 5 pi over 12 goes with the small wheel. Okay, so now I kind of want to encourage you to see if you can finish this problem really on your own. I know sometimes people get a little irked by applications, but you'll never get better at them if you don't try. So the worst thing that happens if you try is that you might get a little frustrated, or your pride might be a little sprained that you didn't get it right. But like, math is really no place for pride. Math is just math. It's not, people get very emotional about it, but you don't, like, it's not actually saying anything about you. These are tough problems. So here's the deal. We want to figure out what is the arc length for the smaller wheel. You can do this, okay? So figure out the arc length for the smaller wheel. You know how much it rotates and you know the radius of it. So maybe pause here and go ahead and do that. Okay, so I've got S equals R theta. So I know that the radius is 4.13, and then I know that it rotates 75 degrees, so I can figure out this arc length no problem. Okay, so the only thing I want to point out to you is that I'm leaving this in kind of this general fractional form because I'm going to have to use this in a moment. Okay, so here's how we figure out the larger wheel, and this is where I'm really going to push you now to try to finish this on your own. Remember what I said. I said that the arc length traveled has to be the same for both of these. So using our arc length formula one more time, and knowing that the arc length has to be the same for both of these, you have enough information now to figure out the radius of the larger wheel. I challenge you to pause the video and see if you can finish this. If the worst thing that happens is you're wrong, you will learn way more from this video if you actually try. Okay, so the arc length has to be the same. So what that means is this has to get plugged in for S, and then I know what theta is, right? Because I know how much it rotates. So I know what my S needs to be, and then I know what my theta needs to be. And that will allow me to find my radius. So I plug in my S and I plug in that theta that we found, and now it's just solving for R. So if I go through and I solve for R, there you go. So my R is going to come out to 6.88 centimeters. Remember your significant digits. Okay, for the last one, so I've got a little illustration here. So how many inches will a small weight rise if a pulley is rotated through an angle of 65 degrees in 15 minutes? And then through what angle to the nearest minute must the pulley be rotated to raise the weight 12 centimeters? Okay, so there's kind of a lot going on here. And I want to start with just the first part of this. So how many inches? Oops, I said inches. I should have said centimeters. Let me change that. Okay, sorry about that. All right, so I've got this pulley. So I've got some string or rope or whatever attached to it, and the pulley's going to go this direction to bring the weight up. Okay. Now, you know that this is going to have to do with arc length. We've seen some other application problems like this, right? So when we talk about how many centimeters will this weight rise, well, that has to do with really the arc length that it travels around this pulley, right? So I've actually just basically told you how to do this. Like, you basically need to figure out how much this rope is moving up, and you know the angle and you know the radius. So I think you can figure out this first part. I would challenge you to see if you can do this, okay? And then hit play when you're ready. Okay, so obviously we need to convert to radians. Now the only thing that's weird about this is that going from radians with minutes, I want to just convert that to a decimal. I think it just makes the conversion a little easier, because then I can write it out like this. So if I multiply these things together, I actually can get a simplified fraction of 29 pi over 80. So I'm just going to note this, like, so this is going this way and it's going through an angle of 65 degrees in 15 minutes. So it's starting here and then it continues up to until like this reaches 65 degrees in 15 minutes, and this is the equivalent radian measure. Okay, so like I said, so if you were stuck on that, maybe consider now trying to finish this out, because we really just have an arc length problem. So I think you can finish this. So again, consider pausing and hitting play when you think you've got it. Okay, so right, so now I have my radius 8.13. I've got my my radian measure, so just bada bing, bada boom, multiply them together, I get 9.26, no problem. Okay, so this is really part one. I'm just gonna note that over here just in case we need it, because I'm just kind of working through this on the fly. Okay, so now let's move to the next question. So through what angle to the nearest minute must the pulley be rotated to raise the rate 12 centimeters? Okay, so we know that the weight already went up 9.26 centimeters, and now I want to figure out how far do I have to rotate this pulley to go up 12 centimeters. Okay, so think about what this 12 centimeters actually is. Like, what does this represent? So I know that it would go up 12 centimeters this way, but we're thinking about this in terms of arc length. So what does this 12 centimeters mean? It means that we want our arc length to come out to 12 centimeters around. That's like what we would want, because then this weight would raise that high, okay? All right, so I think you can figure this out. You have the arc length formula, you know your radius, you know what S you want. Again, I would challenge you to finish this. So I'm going to use my arc length formula, and I've got to plug in 12, and then I've got 8.13 theta. So now I've just got to figure out what theta is. No problem. I'm just going to leave it in this fractional form so I get a more exact answer, because I need to convert this to degrees. So I'll go ahead and take my 12 over 8.13 radians, and then I will convert that to degrees. So I get this crazy looking thing. Now this did say that we wanted the nearest minute, so then I just have to convert, which I'm going to skip over how to do the conversion. I'm assuming that you know how to do that, or you have a calculator that can help you do that. I have videos where I show you how to do that, but I'm going to skip over that for now. And so that's it. So it's a pretty straightforward problem, actually. So if you found this helpful, consider liking this video or leaving a comment, sharing, or subscribing. And otherwise, thanks for watching, guys. I will catch you next time.